like carbon, nitrogen, oxygen. What would the molecule between carbon, nitrogen, and oxygen look like? So what we want to do is we want to take carbon, nitrogen, and oxygen, and look at the periodic table and say how many electrons on each of these atoms. So carbon has 4 electrons. Nitrogen has 5. Okay. Oxygen has 6. So probably ain't going to happen because it's an odd number. So we probably need an extra electron. So we just throw an extra electron on this thing. So with that, what is the correct structure for this anion? All right. So what I want to do is I want to add all these together. So it's going to be 10 plus 6 is 16 electrons. So where are the 16 electrons? Well, the very first thing I need to know is which one of these is the central atom. Carbon. Why carbon? Yep, it's the lowest electronegativity. So it's going to be carbon, and it's going to have its electrons. And I'm going to throw a nitrogen in there. Let's go ahead and use color. And I'm going to throw a nitrogen in there with its 5 electrons. And I'm going to throw an oxygen in there. Oops, green since I have it. Throw an oxygen in there with its 6 electrons. And throw an extra electron in there. Okay? So is that a happy molecule? Well, no, it's not a happy molecule. Because those 3 atoms are going to obey the octet rule. So how do I get these to obey the octet rule? Well, there's a couple different ways I can do this. One is I can bring that electron down, that electron down, that electron down, and that electron down. So one option of this molecule looks like this. Okay? So there's one option. The other option of this molecule is to bring a pair of electrons down here and put those on, and so I could have this. Okay? And finally, I could actually bring all these electrons here down to the 2 pairs here and leave 2 pairs on there, and I could form this. So then the question becomes, those are all valid Lewis dot structures. They're all valid Lewis dot structures because they all have, I have my 16 electrons, and they all have 8 electrons around them. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, etc. So the question is, how then do I know what the correct structure is? Or more likely, how do I know what the structure is? We'll talk about resonance, but yeah, there'll be a little bit of each one, but one's primary. And how do I know that? How am I going to be able to tell that? How? How? The formal charges, right? So the formal charges. So if I do the formal charges for this, what you'll see, formal charges on this, come on. Oh, there we go. So here are my possibilities. Okay, again, all -1 charge. Those all have -1 charge. Is it better to have nitrogen with its 3 lone pairs, or oxygen with its 3 lone pairs, or something in the middle? So what I'm going to do is I'm going to go back and calculate my formal charges. So here's the way this works. Actually, it's not very hard. Oxygen is going to be 6, because it has 6 electrons. 6 minus 1 gives us a -1. Okay. Carbon is 4 minus 4, so carbon's happy, it's 0. And nitrogen here is going to be 5 minus 2 minus 3, so nitrogen's going to be 0. Oh, that's pretty happy. Okay. Oxygen here is going to be 6 minus 4 minus 2 is 0. Carbon is 4 minus 4 is 0. Nitrogen's not very happy here. Nitrogen is 5 minus 4. Okay, 5 minus 4 minus 2 gives it a -1. Oxygen here is going to be 6 minus 2 minus 3 is negative 1. Carbon is 4 minus 4 is still 0. This nitrogen is really not happy. 5 minus 6 minus 1 is negative 2. Okay? So not a very happy molecule. Positive 1. Sorry. Positive 1. Okay? So which of those is the best and why? And we want to take a stab at it. Anybody want to be brave? Yes?
The first one, because the negative charge is on the most electrons.
Okay, perfect. This is your primary structure for that anion exactly because the electronegativity, the most electronegative element prefers the negative charge. Oxygen prefers to be the more negative atom. This has the electrons on the preferred electronegativity, most electronegative element. Which one is the worst of these? Yeah, this guy over here is horrible. When you start to separate charges from each other, you're going to be really, really low on the probability index on that one. Okay? Would this one be around? Yeah, maybe a little bit. Maybe a little bit of that. But most of the molecule will look like this. Okay? Which does lead us into the theory of resonance. Okay? Now, resonance is one of those theories that literally is a band-aid or a patch on a theory that doesn't really work. Okay? So that's why we have to actually look at this in this which one of these does it look like? Well, it really looks like this one, but it also has a little bit of this one in it. Not much, but mostly this one. And so the theory of resonance, what's really important about resonance, especially when we get into organic chemistry, is resonance is one of those concepts that oftentimes it's not fully grasped. And so therefore when we get into organic chemistry, it's really hard to reteach that. So really pay attention to resonance for a second. Resonance is the movement. So resonance is the movement of pi electrons and lone pair electrons. Okay. That is so important for you to just memorize. Resonance does not break up sigma bonds. Sigma bonds are single bonds. Pi bonds are double bonds or triple bonds. This is a sigma bond. That's a single bond, sigma single. This is a triple bond. It has a sigma bond in it and 2 pi bonds. Sigma bond, 2 pi bonds. This is what we call a double bond. It has a sigma bond and 1 pi bond. This is a double bond. It has a sigma bond and a pi bond. This is a triple bond. It has a sigma bond and 2 pi bonds. This is a sigma bond. So what you've seen with these is we've moved only, we have not broken up sigma, 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 sigma. We have not broken up. We haven't moved atoms around. What we have done is we have moved electrons that are lone pair electrons and pi electrons only. Okay? So when I calculate the structure for something like ozone, ozone is an interesting molecule. Ozone is O3. Okay? There are 2 ways to put together good Lewis dot structures for ozone. Let's talk about them. One way is to do, so 6 times 3 is 18. So 6 times 3 is 18 electrons. So I need to worry about 18 electrons. One way to do it is to do this. 18 electrons, right? 2, 4, 6, 8, 10, 12, 14, 6, 2, 4, 6, 8, 10, 12, 14, 16, 18, okay? So every oxygen in that molecule has an octet. I have all 16 electrons accounted for, okay? The other way to draw ozone is this here. Again, all of them have an octet. 2468, 2468, 2468. Okay? Totaling 18 electrons. Now, with that, notice this one has a 0. Every one of these oxygens has a formal charge of 0. Right? 6 minus 4 minus 2 is 0. 6 minus 4 minus 2 is 0, etc. So these are all 0. Looks happy. Here, I'm 0, but notice here, I'm positive 1, and out here I'm negative 1. So you might be thinking, the one on the left really looks good, doesn't it? Because it has everything accounted for. Everything, all octet, all have an octet, excuse me, all have an octet, all have a 0 formal charge. That looks pretty good. But here's the problem. Experimentally, we know ozone doesn't look like this. Okay? Even though it's a good Lewis dot structure, it doesn't look like this. We actually know it looks something like this, but it doesn't look like this. And that's frustrating. And that's because the Lewis dot structure is a theory that breaks down. And so we have to have a Band-Aid. And the Band-Aid is called resonance. Because one of the things that I want you to see is this is where these little sticks and these dots break down. What happens with ozone is when you look at ozone, if it looked like this, you would think, oh, okay, well, we'll see this here with bond enthalpies in a second. We're going to come back to thermochemistry. With an elongated or a single bond, this is a longer bond than a double bond. So experimentally, I should see a long bond and a short bond, but I don't. In fact, I see some length of that bond in between a single bond and a double bond. What's going on with that? Well, here's what happens to ozone. Resonance is the movement of pi electrons and lone pair electrons. Not single bonds, not sigma bonds. This has a sigma bond and a sigma bond and it has a pi bond. So watch what happens. If I take this lone pair of electrons and move it down between the oxygen says, I can't have 10. Oxygen has to have 8. So oxygen says, cool, go ahead and put it back on me over here. Okay? And so what happens is we have a double-headed arrow. It's a very special arrow. It's a resonance arrow. And so it looks like this. With a positive 1, excuse me, a plus 1, and a negative 1. And so this one over here says, okay, well, right on, I'm going to go ahead and send those back over to you. Okay, I'll send those back over to you there. And so then over here it says, okay, I'll send, and so it's going back and forth and back and forth and back and forth. That's resonance. You see, here's the cool thing about resonance. It's where the theory of Lewis dot structures breaks down, because ozone doesn't look like this, and ozone doesn't look like this. Ozone looks something like this. But we don't like that. That looks crunchy. That doesn't look cozy. That doesn't look like my little perfect octet that I've learned. But that's what it looks like. And here's the way to think about resonance. If this were yellow and this were blue, you would not see yellow or blue for ozone. You would see green. Okay? It's somewhere in between. And we don't like that, because it's a little unsettling. All right? So the correct structure for ozone actually looks not like that, but like that. And experimentally, we know that these bonds are identically the same length, 1.278 angstroms. That's shorter than a double bond, and it's a little bit longer, or excuse me, shorter than a single bond, a little bit longer than a double bond. So it is somewhere in between. And so ozone, again, and we put brackets around this, okay? And we say ozone looks like that. There you go. It looks like both of those together. Not this or this, both and. Okay? And that's the theory of resonance. What did I do? I moved only lone pair electrons and pi bonds. See how that works? So watch. When we mess with higher anions and cations, we see this. All right, again, those bonds are there. There's that little graphic. If we take blue and yellow, it makes green. So ozone looks like the combination of those two. All right, and again, it looks something more like what I had up here with a little bit in between both of those. All right, those are resonance structures. Okay. Again, I can't emphasize this enough. Lone pair electrons and pi electrons are all that's moving. You're not breaking the molecule up. You're just moving these electrons around. They're buzzing around out there around the structure of this thing. Okay? So that's what's happening with resonance. If we take something like the carbonate anion, the carbonate anion is going back CO3 2 minus, right? We know that CO3 2 minus. That's the carbonate anion. What does it look like? Well, that's a great question. When I actually take my 4 electrons plus my 3 times 6 plus my 2, okay? So that's going to be 18, 19, 24. Where do I put those 24 electrons? Well, carbon's the central atom. So I'm going to put carbon and oxygen, and I'm going to have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8 for a total of 24. Carbon is not happy. Carbon needs 8. So 1 pair of electrons comes down, and so the correct structure for carbonate appears to be this. Okay, and it's a 2 minus. Now here's the problem. It's a 2 minus. Here's the problem. It doesn't look like that. Why? Because when you actually take the geometry, the physical geometries of the carbonate, all these bonds are the same length. And if it looked like this would be shorter, and these two would be longer. It doesn't look like that. So what's going on? What do you think the answer is? Yeah, probably what we had written up here or up there, resonance. So watch. Here's what happens. Pi electrons, lone pair electrons. Oh, well, one of them does that. So that resonates to this. Okay, and the next one says, oh, okay, well, that's one option I could do. The other option I could do is I could bring those down to there and kick those up there. See how I'm only moving pi electrons and lone pair electrons. And it looks like that would move there and that would form this. Okay, and I would ask you, what does carbonate look like? And the answer is all 3 simultaneously. Yeah.
So, can you tell the difference between when a molecule has a moving pi bond and then just that molecule rotates? Are those distinguishable actually?
They are not. They are not.
So you can just rotate something and that can be almost equivalent to changing the
Ish. Pi bonds don't rotate.
Right, but if the whole molecule rotates and then that becomes an isomer, or at least a resonance.
Resonance form. Yeah.
So isn't like resonance almost like a molecule?
Well, see, here's the problem. Yeah, this thing doesn't look like this. That's where you're seeing the breakdown of the theory, right?
The other thing is like, where do you slice time?
Yeah. Actually, you do have a limit. Would you say where do I slice time?
Yeah, well, I mean, like, say
Yeah, you have a limit there.
Going big, small, big, small, big, small, big, small.
Yeah.
And it's alternating so quickly that to you,
It's just one. Well, and here's the thing. I don't personally like thinking of carbonate like this. I like thinking of carbonate using my little magnetic blobs. This is what carbonate looks like. There you go. That's a much better picture of carbonate than either of those. Okay, but again, that doesn't set well. So what does sodium carbonate look like? Sodium carbonate then would look like that. The sodium just comes into the carbonate. So, but we like letters, electrons, and bonds, you know? So anyway, that's where, so you're seeing that breakdown of the theory, and it's just not a good explanation other than magnetic lava lamp theory. Okay? Benzene's a killer example of this. Benzene doesn't look like that, and benzene doesn't look like that. So oftentimes we abbreviate benzene with a circle in the middle. Okay? So it's just literally the C of 6 pi electrons out of the 2p orbital. It's super cool when we get into organic chemistry, and I get to teach about aromatic chemistry, which is really fun. Okay? So here is the formate anion, and you can see, oh, okay, what am I going to do? I'm going to move those electrons there and those electrons there, and oh no, I'm going to move those electrons there and those. Oh, I'm going to move, and it's going back and forth. Okay, so it's both of those, not one or the other, and that's the picture that we kind of want to get. Okay, that deals with resonance. All right, delocalized electrons. Okay, a couple different exceptions to the octet rule. I like to think of it again as there's 4 atoms that never violate the octet rule, and the rest of them are kind of all over the place. Most try to behave nicely. Phosphorus and sulfur try to obey the octet, but they don't necessarily play nice. Depending on what's around them, they can violate it, and they often do. So there are a few odd examples of molecules with odd numbers of electrons, like nitrogen oxide or nitrous oxide would be the example. When you have 5 electrons for nitrogen, 6 electrons from oxygen. Typically, these odd number of electron molecules aren't very stable. Carbon monoxide is, but again, it's got some issues. There's some molecules that have less than an octet. I already showed you an example of that with boron. I have another example up here. And then there's quite a few that actually have more than the octet. Phosphorus, sulfur, and chlorine, for example, really, silicon for the most part does obey the octet, but it also has electrons down there in the 3p, so it can also violate that if it wants. All right, here's some examples of odd numbered electrons: nitrous oxide, nitrogen dioxide, and you can see a chlorine dioxide. So these have an odd number of electrons. It's just some examples of actual entities that do not obey the octet rule. Fewer than 8 electrons. We already did this with boron trifluoride. We saw that if we calculate the formal charge on boron, none of these are really happy. So more than likely, boron just has 6 electrons, and that's true. Here's the cool thing about boron, though. Boron has a 2p orbital that has the ability to accept electrons into it. And so boron behaves as a really good Lewis acid. And we'll talk about that in organic chemistry, because we have things like sodium boryl hydride, lithium aluminum hydride, these atoms that actually capitalize on the fact that they only have 6, so they can accept 2 more to make 8 if they need to. So that's really something really kind of cool with BF3, okay, or boron itself. It's a really neat, fun molecule to work with. So here's what we think really does look closer to boron trifluoride than any of these, and you can see I like the way this is written. More important resonance, less important resonance structure. Okay? Cool. All right. Let's go ahead and do one more. Let's predict the structure for phosphorus pentachloride. So if I do phosphorus pentachloride, I have phosphorus with its 5. I have chlorine with its 7. So 5 and 7 times 3. So phosphorus pentachloride, so PCl5. I have 5 plus 5 times 7. So that's going to be how many? Should be 40. So 40 electrons. All right. So where do I put those electrons? Well, phosphorus is the central atom. So I'm going to put a chlorine, a chlorine, a chlorine, a chlorine, and a chlorine. And I'm going to put my electrons around it. Okay. So what's 8 times 5? 240. So let's calculate the formal charge on phosphorus here. Phosphorus is 5 valence electrons, minus half of 10 is 5, so it's happy. Its formal charge is 0, and all the chlorines are 0, and so this molecule is what it is. So phosphorus can violate. So phosphorus either will make 5 bonds or 3 bonds. Because remember, nitrogen always makes 3 bonds. Phosphorus can make 5 or 3. And so we see the structure of that. And when we get to the next chapter in with Vesper, we'll see that that's a trigonal bipyramidal geometry. And that becomes pretty cool when we get to build on this concept of where are the electrons around certain structures. And so there you see phosphorus pentachloride in its trigonal bipyramidal geometry. Okay? So phosphorus has 10 electrons. It violates the octet rule. Sulfur prefers 8, but it also can have 12. And so again, it's one of those that violates the octet rule. And so this is why when you see something like phosphoric acid, so what is phosphoric acid? Well, phosphoric acid is H3PO4, right? You know that now. That's phosphoric acid. What does phosphoric acid actually look like? Well, phosphoric acid actually looks like this. If you did a good Lewis dot structure, it looks like that. And how many electrons are on phosphorus? 10. And it's happy. Okay, so that's what phosphoric acid would look like then. All right? Cool. Good stuff, right? Okay, so typically when we jump down to the third row, that's why silicon, phosphorus, sulfur, and chloride can accept more than 8 electrons. That's what's going on there. And I'll explain that when we get into hybridization theory, because you're going to see there's a mixing between the 2s2, the 2p2, and the 3d. And so we'll talk about that when we get into hybridization. That gets kind of fun. So again, we're going to put some electrons in that d orbital, that 3d, which we don't have from carbon, nitrogen, oxygen, and fluorine, which is why those don't have that d orbital to put electrons in, so they don't violate the octet rule. Okay? So if we look at PO4 3-, you see it right here. This is the phosphate. If I put protons all the way around it, you can see that that is how we would predict the structure of the phosphate to be happy. And so if I put protons on all of this, I put hydrogen, H plus is here, H plus here, H plus here, you have phosphoric acid. Okay? And so that's where those electrons are going to go. All right? Kind of cool. Now, this chapter ends with this. We go back to a little bit of entropy. And the reason why we talk a little bit about entropy at the end of this chapter is because there's another way that organic chemists will actually use the idea of the strength of bonds to calculate enthalpy values for reactions. So an example of this would be something like burning of methane. If I burn methane gas in oxygen, what am I actually doing? Well, I'm actually breaking bonds and forming bonds. What if I take something like methane and convert methane into chloroform? Well, methane into chloroform is the breaking of 2 bonds and the forming of 2 bonds. So theoretically, if I knew the energy associated with the breaking of the bonds and the forming of the bonds, I could tell the overall enthalpy of the reaction. That's what we use in these bond, the bond enthalpy calculations. So bond enthalpy becomes really important. And again, this is where you just have to keep track of how much energy in the reactants and how much energy on the products. So what happens here is we're going to calculate bond enthalpy. How much energy is associated with a chlorine-chlorine bond? Well, all this has been calculated for us. We know it. We now have it in tabulated data, in tabulations. So the bond breaking of a chlorine bond is 242 kilojoules per mole. So if I know from a table how much energy is associated with certain bonds, then I should be able to use Hess's law to calculate the overall enthalpy of a reaction. And that's what we're going to do right now, because it's so fun. And you loved your enthalpy. I know you guys love thermochemistry. It's one of the favorite chapters of this whole semester. I know that. I just know it. So before we jump into the beautiful thing of Hess's law again, I just want to point out, look at the bond energies associated with single bonds and double bonds. So here you have carbon-carbon single bond, 348 kilojoules, okay? Look at the carbon-carbon double bond. Oh, a lot more energy, all right? 614. Look at a triple bond, 839. That's a lot of energy associated with, which is why If anybody in the room has ever cut metal with acetylene gas, anybody ever done that? Oxyacetylene tank? A torch? The red tank and the green tank? No? Well, it's a torch. Okay, so you haven't cut metal. Here you haven't really. We use in oxyacetylene torches, they use, what I have in my shop at home, is we have acetylene gas. This is acetylene gas. High amount of energy associated with this gas. Notice we don't use ethane gas, because look at ethane gas has how much energy associated with it, 348 kilojoules. Acetylene, look at how much energy, potential energy it has, 839. So we don't melt metal with propane or ethane or methane. We typically use acetylene, which has a lot more energy in it. Yeah, kind of cool, right? So you can see that right here with that energy association. Two other notes on this chart. Look at your two strongest bonds. The two strongest bonds are carbon monoxide and nitrogen. That's an important little thing to note. So here's carbon monoxide, a very strong bond, a carbon bond between an oxygen. Okay, those 6 electrons being bound between the carbon and the oxygen. And up here we have one of the stronger molecules known, and that is nitrogen, N2 gas. Very inert gas, meaning it's very happy by itself. It doesn't like to react with much. Okay, and we use it in our lungs, of course, because most of the air that we breathe is around 80% oxygen, and so it's just a gas that goes in and comes back out. The exception of that is if you do scuba diving, there's what they call the bends. If you come up too quickly, when you're under pressure, so every 33 feet underwater is 1 atmosphere. It's the same amount of weight that the atmosphere has from up in the stratosphere to the surface of the ocean. That's called 1 atmosphere. We'll see this when we get into gas laws. If you go 33 feet underwater, that's in 1 atmosphere. Okay, if you go 66 feet, that's 2 atmospheres. You go 99 feet, that's 3 atmospheres. So all that water is pushing down on you, and what happens within your body is it starts to push the nitrogen out of your tissue into actually out of your lungs into your tissue, out of your blood into your tissue. So if you come up too quickly, those little nitrogen bubbles get trapped within your tissue, and it's called the bend. It's very, very painful. And so the only way to get it back into your system is to go back down and push it back out, or send it into a hyper tank thing that they pressurize. But anyway, that's something. If anybody's ever scuba dived, it's kind of a cool thing to do. Okay, so here's what we're going to do. This is an important thing. Note these are average bond enthalpies, and that's important because a carbon-hydrogen bond is not necessarily the same on all molecules. For example, the carbon-hydrogen bond here is going to be slightly different than the carbon-hydrogen bond here. So these are averages. And that is an important thing, and you see that here. Carbon-hydrogen bond on methane is going to be slightly different than the carbon-hydrogen bond on chloroform. So again, these are averages, not absolute. But overall, it gives us an idea of the endothermic, whether we're talking about endothermic or exothermic reaction. So let's see how to use this table. It's not that difficult. Again, this is just adding and subtracting, but and multiplying. I do have to keep track of who's going where. That's all we have to do. So let's say that I know how much energy is associated with the breaking of a chlorine-chlorine bond. Well, I know that because it's right here. Chlorine-chlorine bond is right, where'd it go? Right there, 242. Formation of a carbon-hydrogen bond, or the breaking of a carbon-hydrogen bond, is 413. So if I go back over here and I say, oh, well, I know how much energy it costs to break a chlorine-chlorine bond. I know how much energy it costs to break a carbon-hydrogen bond. So I have a hydrogen floating around, and I have two chlorines floating around. I can then recalculate how much energy is given in a carbon-hydrogen or a carbon-chlorine bond and a hydrogen-chlorine bond. So that's what we're going to do. It's simply just adding and subtracting. So knowing that, here's the good old Hess's law that everyone loves so much. So I'm going to summarize the bond enthalpies of the bonds broken, and I'm going to subtract that from the summation of the bond enthalpies of the bonds formed. And it's not difficult. You just have to pay attention to where the numbers are. So let's do that. Let's calculate how much energy it costs to break a carbon-hydrogen bond. Add that to the amount of energy it costs to break a chlorine-chlorine bond. Subtract all of that from the amount of energy I get back when I make a carbon-chlorine and a hydrogen-chlorine bond. So here you go. Methane plus chlorine gas goes to chloroform and hydrochloric acid. So here I have 1 carbon-hydrogen bond and 1 chlorine-chlorine bond, and I'm forming 1 carbon-chlorine and 1 hydrogen chloride, okay? So, hydrogen, these are, those the enthalpy of carbon hydrogen, what is that? Well, it's right there, 413, so I plug it in there. What is the enthalpy of chlorine? Well, it's right there, 242, so I plug that in there. What do I get back when I have a carbon-chlorine bond? It's gonna be somewhere right about there, 328, okay? And the energy associated with the hydrogen-chlorine bond is gonna be somewhere right here, 431. So if I take 413 out of 242, I get 655. If I take 328 out of 431, I get 759. I subtract 759 from the 655, and notice, it's an exothermic reaction by 104 kilojoules. So if I add methane gas and chlorine gas, I do have to add a little bit of a spark, by the way, to get that to go, but once I do, it's an exothermic reaction, once the reaction gets going, okay? And I know it's I know it takes a little energy to get it going because I have to break the bonds. And so if you just put methane and chlorine gas together, they don't do anything. They actually behave pretty nicely. Put a little spark in there, now you'll suddenly you get a reaction out. Okay? All right. So we can summarize all this. Now, last thing I wanted to show you is a trend that's also a very important trend, and that is bond lengths. So I was, when we were talking about resonance with electron and lone pair and pi electrons moving around, notice the bond length of a carbon-carbon bond, 1.54, okay? Notice the length of a carbon-carbon double bond, 1.34. Okay? Notice the length of a carbon triple bond, 1.21. So what's happening is single bond, double bond, triple bond. It's being pulled in. Go to our oxygen here and remember these numbers, 1.48 and 1.21. Let's write those down. 1.48, so oxygen single bond is 1.48. Oxygen double bond is 1.21, okay? If you go back, and if we go all the way back to ozone, notice what ozone is. Ozone is right here. 1.27. Huh. And that's one of the confirmations that we know there is a resonance form of this because it's longer than a double bond and shorter than a single bond. Okay? And that's how we confirm that ozone really does have that structure because that is the actual dimensions for that ozone molecule. Okay? Isn't that kind of cool? So you're actually seeing where that plays out. All right. So with that, the only other one I wanted to show you is right here, is the carbon-oxygen family. Now, what's going to happen with the carbon-oxygen family, we are going to see when we get into some carbon chemistry, especially next chapter when we get into Vesper, that there is something special about the carbon-oxygen double bond. So that's one to just take a note of. It actually is a bond that we deal with. We have an entire semester in organic chemistry called Organic 2 that deals with the carbon double bonded to an oxygen, which is how special it is. So carbon double bonded to an oxygen, like this, is a really special bond. And if I draw my Lewis dot structure, that's what it looks like. That's formaldehyde. Some of you might have heard of formaldehyde. But here's the crazy thing. I can draw a resonance structure from this, so watch. I take my blue pen, which is my resonance pen. I can take these electrons, the pi electrons, and push them back up onto oxygen, and I can form a resonance structure for formaldehyde. And it looks like this. Minus and a plus, okay? That's a resonance structure for formaldehyde. But here's the thing. I don't necessarily want an entity that has charges. If I have an octet rule with no charges, I'm a better structure. So what happens with ozone, ozone doesn't necessarily look like this or like this. It mostly looks like this, but it does look a little bit like this. And because of that, if I am negative, if I am a nucleophile, nucleus loving, I love protons, I love positive, I'm nucleophilic, I love that carbon. Okay? Because that carbon is a magnet. It's a negative, it's a positive end of a magnet. And if I'm the negative end of a magnet, I'm going to attack. And that is organic chemistry. Okay? So you see the importance of some of these distances or measurements up here that we use in general chemistry actually become very important when we start to apply organic chemistry or chemistry in general in the real world. Okay, so typically as the bond order increases, bond order of 1, single bond order of 2, single and double bond order of 3, single bond and 2 double bonds, I shrink that distance. That distance is decreasing. Okay, and so our multiple bonds down here, something like the nitrile or the cyanide is what that's called right here. You can see that bond order as it increases sucks those electrons in up here with the bond lengths. Okay. Any questions on that? Yes.
Will we be required to memorize?
Yep. You have to memorize all of those. Yeah, I'm really a big fan of memorizing tables.
Oh,
That's not my thing. I like to ask the question, how does that work? Not what is it? So not a big fan of table memorizing. My 13-year-old is actually memorizing the periodic table in his science class. Why? Why? Don't do it. Oh, he's so cute. He's all the way up to Argon. Yeah. Okay. Any questions? Want me to go back over? Anything you want me to resolve? Because Workday Friday is ahead of us. We're going to apply resonance. We're going to apply formal charges. We're going to use Lewis dot structures, and then we're going to move on in on Monday into VSEPR, valence shell electron pair repulsion theory. Okay? Good? Nothing? Yes?
when you calculate the formal charge to the first number,
Yes.
that was just how many
Valence electrons.
valence electrons?
Correct. So that's the number up here. So 7, 6, 5, 4, 3, 2, 1. Yep. Yep.
And then, how do we calculate like the one?
No, you won't. Focus on the first 3 rows. We really, this is really where our wheelhouse right here for moving into. Okay, good. Alrighty. Have a great rest of your Wednesday, and I will see you on Friday, as long as there is a Friday.